Okay, so let me briefly go back to the previous lecture for the benefit of those who did not attend the lecture. So welcome to our lecture. We are going to talk today about quantitative analysis, essentially measuring things. Quantitative analysis is a form of data analysis. We are going to see different forms during the course. In particular, this week we are going to talk about statistical analysis. That's what I'm going to do today. And on Thursday, we will see a guest lecture by Dr. Dario Dinucci about applications of machine learning to software engineering. So the notion of quantitative analysis comes from the word quantitas, which has been coined by Cicero, and it comes from quantus, how much, and tas, which is essentially like et, like in English, elitis and so on. It's a calque of ancient Greek. So the core notion of quantitative analysis is a notion of a measure or a notion of a metric. And in general, it's a mapping from some kind of software engineering artifact to a well-known domain. In this course, you already have seen several such measures. For instance, we can say that measuring activity in a certain brain area, or asking questions in a survey, or analyzing software repository, all those things tend to produce numbers or tend to produce values from a well-known domain. In general, domain is a collection of values which we can count, right? So it's quantus, right? How much? The values are often numerical, but not necessarily always so. So here you see examples of 3 domains. On the left, you see programming languages. On the right, you see sites of different code base in lines of code. So for instance, you can see that the source code of a large hadron collider consists of 50 million lines of code, while car software of a modern car, average modern car, is more than 2 times bigger. And in the middle, of course, you see 3 smileys: happy, neutral, and sad, or positive, neutral, and negative, which can be used for the sentiment analysis experiment, like the one we have discussed last week. So why have I chosen those domains in particular? This is because they are representative for 3 types of domains. On the left, we have the nominal domain or nominal scale. Essentially, the nominal domain boils down to labels. The only thing we can actually say about 2 programming languages is whether they are the same or not. So there is no natural order between programming languages. Ordinal domain or ordinal scale is all about the order. It's all about an ordering over values. This ordering is somehow natural. Also, it's not necessarily unique in any sense. As long as we agree, we are fine. So for instance, we can say that neutral is between negative and positive without necessarily agreeing whether negative is less than positive or negative is larger than positive. What's also important is that we cannot talk about the distance on the ordinal domain. So we cannot say that the distance between the negative is the same as between neutral and positive. There is no notion of distance. So interval, ratio, and absolute are all numbers. There is a difference between the 3. I'm going to explain it in a moment. But for the largest part of this lecture, they are numerical domains, and it is sufficient for us to know that they are numerical domains without distinguishing between interval, ratio, and absolute. Strictly speaking, interval has a notion of a distance, and ratio not only has a notion of distance, but a clear 0 and a clear 1, a clear 100%. So for instance, if you are talking about percentage of people of a certain gender in a project, or percentage of commits performed by a specific developer. So those are typical examples on the ratio scale. Finally, absolute is an absolute measurement, something which is completely determined by your computation procedure, for instance, the number of developers. But as I already said, for many practical purposes, those interval measurements, ratio measurements at absolute scales are all numbers. So we are not going to distinguish between the three. Okay. So the next question is, of course, what do you want to do with our measurements? Do we merely want to report what we see? So in this particular case, do we want to report that we have 2.5 bananas? Or do we want to derive some kind of conclusions about bananas in general, about the broader context? So you might recall our discussion of sampling from lecture 3. We usually study a small group of objects or people with the intention of inferring conclusions about a much larger group of objects or people. So we start by studying sample, and we would like to derive conclusions about the population. So if our goal is only to describe what we see, we are going to use descriptive statistics. If our goal is to derive conclusions about larger populations, we are going to use inferential statistics. Most of the time, we are interested in inferential statistics. However, before performing inferences, it is considered to be a good practice to describe the sample we have taken. And that is where descriptive statistics comes handy. So here we have a quote from a paper by Gregorio Robles and his co-authors about Debian 3.0, and specifically about the number of packages and number of lines of code. So let me ask you whether you consider this to be a statement which can be classified as ordinal descriptive A, ordinal inferential B, numerical descriptive, or numerical inferential. Roughly half of the answers are submitted. Okay, so this statement refers to numbers, such as the number of packages of the source code and the number of lines of code. It's a numerical measure, and it does not try to make any inferences beyond the specific data which has been done, beyond the specific version of Debian. So the correct answer here is C. It's a numerical value and it is descriptive. So what we are going to do in the remainder part of the lecture, essentially we are going to try to fill in this table. So we have nominal, ordinal, and numerical interval ratio absolute as columns, and we have descriptive and inferential as rows. And what we are going to do, we are going to start with nominal descriptive, and then we will go for nominal inferential, then we will consider ordinal scale, and then we'll finally consider interval ratio and absolute. I have to stress that the amount of statistical techniques which can be applied to study software engineering phenomena is enormous. And it would be completely preposterous for me to expect that I can teach you all of them in 2 hours of the lecture. My goal is merely to introduce you to some techniques which are used quite often. You might be familiar with some of them. You are probably not familiar with the others. And of course, I can only encourage you to dive into literature. I will mention some books at the end of the lecture, which can be useful for your study. So let us start with the nominal domain. So when it comes to describing the nominal data, one usually uses frequencies and percentages. If you like visual things, you can think about pie charts, you can think about tables, you can order those things based on frequencies and so on. So here we see, for instance, the percentage of pull requests on GitHub during the period of July-September 2020, and you see that JavaScript, Python, and Java are the languages. Another example of representing nominal data is the following table. What is interesting here is that we have 2 variables on the nominal scale. One is gender, with women and men. In this particular study, there have been no non-binary participants. And another variable is an interpretation of this emoji. So this was a study where the participants have been shown a series of emojis, including this one with rolled up eyes. And they have been asked an open question: what emotion is this emoji displaying? And then the researchers have manually analyzed the answers received, and they have recognized several basic emotions like anger, disgust, sadness, surprise. They have indicated things like person who essentially believes that this emoji does not represent an emotion, indicates that it was not possible to interpret this emoji. Or essentially, respondents who've been saying that they're not aware of this emoji. Here we see a 2-dimensional table. We see one variable as columns, another variable as rows. We are going to see how we can analyze this data when we'll come to the inferential part. Let us move to the ordinal scale. So when it comes to the ordinal scale, indeed, at the descriptive level, pretty much the same can happen. We still can use our favorite pie charts and tables. In addition to this, we can always use something like a bar chart, simply because ordinal scale is associated with a certain ordering, and then we can use this ordering to position our bars. So in this particular case, we see 3 popular data sets for sentiment analysis, extracted from GitHub, from Jira, and from Stack Overflow. And we have numbers of statements which have been manually labeled as positive, neutral, and negative for each one of the data sets. And you see this ordinal blue, gray, red. In the same way, we can combine 2 ordinal scale variables into a 2-dimensional table. So here we see 2 different sentiment analysis tools called SentiStrength and NLTK that have been used to assess essentially the same theoretical construct. So the theoretical construct here is polarity of a sentiment. So polarity of a sentiment is, theoretical construct is something we usually would like to measure using whatever tools we might have at our disposal. But it is important to distinguish the theoretical construct and the actual measurement, because of course our tools are not perfect and there is no guarantee that they actually capture the theoretical construct we have in mind. Since in both cases we have tools which are supposedly measuring the same kind of theoretical construct, it makes sense to discuss agreement between those tools. Agreement can, of course, also be measured for nominal variables as well, as long as both variables are supposed to measure the same theoretical construct. So in addition to showing this table, we can try to find a way of expressing agreement between those tools. The first measure of agreement is so-called observed agreement, PO, and it is simply the percentage of data points where the tools agree. So we add 17, 96, and 43 and divide it by the sum of all the numbers in the table. The problem is, however, that observed agreement can be high merely by chance. If we toss two fair coins, then the observed agreement will be 50%, but this doesn't really say anything. So the question would be, how much agreement would we expect if the agreement was only due to chance, meaning that the evaluation of NLTK and centistrength would have been completely independent? So to answer this question, we need to compute the expected agreement for each one of the classes under the assumption that the tools are independent. So for example, for the expected agreement for the negative class, we compute percentage of, in this case, data points which have been recognized as negative by NLTK, and multiply it by the percentage of the data points which have been recognized as negative by centistrength. So we assume that those two events are independent, so we can multiply them. And proceeding in the same way, we can compute expected agreement for the neutral class and expected agreement for the positive class, and the total expected agreement is the sum of expected agreements for the three classes. So in this case, we see that the expected agreement is 37.5%, while the observed agreement is 53%. So in a way, it kind of sounds good because our observed agreement is more than our expected agreement. A more careful way of comparing those two values is Cohen's kappa. So Cohen's kappa is defined as a ratio between the difference between observed agreement and expected agreement and the complement of the expected agreement. So in our case, this value boils down to roughly 25%, and this is essentially not such a good news. A common interpretation of Cohen's kappa is shown on the slide, which means that the agreement is only fair. And this is quite troublesome because we have two different tools which are supposedly measuring the same underlying construct, so they should agree, but their agreement is only fair. In terms of the tools, the specific tools which have been studied in this paper, this can be related to different operationalizations of sentiment that the original authors of the tools had in mind. So a very small exercise for you. Here we have a small table comparing performance of tools A and B. Each one of the tools can give yes and no as possible answers, and the numbers are on the screen. As you remember, kappa is computed as a ratio between observed agreement and expected agreement, and the complement of the expected agreement. So here you have 4 options. Okay, so we got several results. It seems that there is a disagreement here. 3 people think that its answer is D, 13%, 2 persons think that it's an answer A, 28%, and 1 person thinks that it's an answer B, 7%. So let's count together. First of all, the observed agreement. So we need to take so we need to compute a percentage of the instances, a percentage of data points where the tools agree. So it's essentially 45 plus 15, the main diagonal, divided by the total sum, which happens to be 100, to make the computations a little bit easier. So the observed agreement is 60%. When it comes to the expected agreement, we need to compute expected agreement for both classes and take a sum. So for class A, we need to take the first row, 15 divided by the total, it's 0.6, and multiplied by the sum of the sum of the first column divided by the total. So it's 0.7. So 0.6 times 0.7 is 0.42. In the same way, we are computing it for class no, for the situation when both tools agree to say no. And there we get the second row, 25 plus 15 divided by the total, it's 0.4. And the second column, 15 plus 15, it's 30 divided by 100, 0.03, the product is 0.12. So the expected agreement is 0.54. This is already an indication that answer C cannot be correct because the observed agreement is higher than the expected agreement. If we substitute the numbers to our formula, we get roughly 3 over 23, which is roughly 13%. So the correct answer was answer D. But of course, not all agreements are the same. You might remember from the last weeks that when we've been talking about controlled experiments, we have distinguished between moderate disagreement, for instance, when one of the tools says neutral and another one says something else, and severe disagreement, when both tools say non-neutral things, but they're disagreeing. So essentially, one tool recognizes the text as positive and another one as negative. So to reflect this importance of disagreement, there is a variant of Cohen's kappa, which is known as the weighted kappa, and it combines the computation we had before with the weighting schema. So if you look at weighting schemas can come in different forms and shapes. This is the most common one. Don't forget that it's again the ordinal scale. And the further the elements are from each other on the ordinal scale, the heavier is the coefficient that has to be taken into account when computing the weighted sum. The regular Cohen's kappa can be obtained from the weighted Cohen's kappa if you put zeros on the main diagonal and ones everywhere else. So in our particular case, I'm not going to bother you with the details of the computation. Kappa drops slightly to 23.2, which is not very big difference. But in general, if we want to make a distinction between kinds of disagreement, weighted kappa is the way to go. Let us continue with our descriptive statistics and let us look at the numerical values. So here we see a distribution that looks pretty symmetric and kind of close to normal. This is a length of the summary lines in the Git log for the Linux kernel. You see that the mean here is around 50. Essentially indicating that when Linux kernel developers are committing their changes, they tend to write roughly 50 lines of explanation. Of course, it's by far not always the case that the numerical values are distributed in such a nice and symmetric way. Most of software engineering measurements do not look like this. Here is an example of a distribution of the number of source lines of code per method in a large corpus of open source Java programs. So please notice logarithmic scale on both axes. So if I would have been showing this on the non-transformed scales, the picture would have looked completely different. This also means that the mean, which we have used in the previous situation, is highly affected by presence of very large values and doesn't really adequately represent central tendency. A median is much more adequate representation in this case. For the same reason, instead of talking about standard deviation, which is a dispersion measure determined based on the mean, we can talk about interquartile range. So just a small reminder for those who do not remember, interquartile range is the difference between the third and the fourth quartile. The first quartile is the value such that 25% of the values do not exceed it. The third quartile, Q3, is the value such that 75% of the values do not exceed it. And the IQR is the difference between Q1 and Q3, and essentially indicating that there are 50% of the values between those 2 points. For our specific example, the first and the third quartile are 3 and 9 respectively, and the interquartile distance is quartile range, is of course 6. So what happens when we have 2 values on 2 variables on the numerical scale? What would be the counterpart of our tables? The common way of showing a relation between 2 variables on the numerical scale would be a scatter plot. On the left, we see a scatter plot showing the amount of functionality in the system on the x-axis. For those of you who have taken software evolution, this is what we call function points. On the y-axis of the left image is the duration of the project in months. Again, please notice the logarithmic scale on both axes. The problem with this kind of visual representation is that multiple data points can overlap. So if in particular, if you have 2 different projects having the same amount of functionality and the same duration in terms of months, those 2 data points will be colliding on the image, and we will not be able to see to differentiate them. A slightly better way of representing this kind of data is a so-called hexagon plot. So hexagon plot is something which you see on the right part of the slide. Each hexagon corresponds to multiple data points with close values, which are all falling together in the area represented by the hexagon. And the color of the hexagon represents the number of data points. So in particular, this means that for the image on the right, we see that around 0, 0, so very close to 0, 0, there are many data points which are falling into the same hexagon. So this particular plot corresponds to relationship between size of a method in terms of Java method in terms of source lines of code and the corresponding cyclomatic complexity. If you do not remember or you do not know what cyclomatic complexity is, it doesn't matter for the moment. It is a measure of complexity of a procedure in general. Of course, in addition to showing this kind of data visually, we can try to characterize the agreement between the 2 variables numerically. And this measure is known as correlation, and specifically as Pearson product moment correlation coefficient. Some of you might have heard about it during their bachelor degree. Just to remind you, if you have, or explain you if you have not, the Pearson coefficient measures linear correlation between two variables. And it has a value between +1 and -1. It is usually denoted as R, and people often report R square instead of R itself. Of course, if there is no reason to assume that the relationship is linear, then one can transform one or both variables using the logarithm scale, which is, for instance, what has been done on both slides, or use on both images, sorry, or use a different correlation coefficient, such as Spearman's rho or Kendall's tau. So in this case, for the second study, also Spearman's rho has been computed, has been reported. Spearman's rho represents degree of monotonic relation between the two variables, which is not necessarily linear. Of course, one might wonder, why do we actually need all those pictures if we have numbers, if we can report correlation coefficients? Unfortunately, the situation is not that simple. This is an artificially constructed example. So there are 4 data sets constructed by Francis Anscombe to demonstrate the importance of graphing the data before analyzing it, as well as to show the impact of outliers and influential observations. So what you see here, 4 completely different stories, 4 completely different pictures, but all standard measures, such as the mean and standard deviation and Pearson correlation coefficient, are almost the same for all the 4 examples, up to 3 decimal places. So when you have a scatter plot, and when you see a correlation value being reported, almost automatically think about images like the one on the upper left, when you have the line and the data points are somehow hanging around it. But it could have equally well be a much more complicated relation, such as presented on the upper left. It might have been an outlier which has influenced the shape, the angle of the regression line, or it might have been a highly influential data point which has completely changed the picture, as in the lower right image. So this is why whenever you are trying to analyze the relation between multiple variables on the linear scale, on the numerical scale, so it's interval, ratio, and absolute, and if you want to understand it, it is not enough to compute correlation coefficients. You actually need to create a scatter plot or a hexagon plot and look at the data. So let me summarize what you have seen so far. So we have looked at descriptive statistics for 3 types of variables: the nominal, the ordinal, and the numerical, interval, ratio, absolute. So for the nominal values, we essentially have very simple things like tables, pie charts. In particular, if you have multiple variables on the nominal scale, tables come handy. For the ordinal domain, we can, of course, show bar charts or any other techniques which would benefit from the ordering of the values on the ordinal domain. And of course, we can also show this as a 2-dimensional table. In this particular case, if we know that both variables actually are supposed to represent the same theoretical construct, it makes sense to talk about agreement. Agreement can, of course, be measured also for variables on the nominal scale. And in this particular case, we have reported Cohen's Kappa and weighted variant of Cohen's Kappa to show agreement between 2 variables on the ordinal scale. And for the interval, ratio, and absolute values, so essentially for the numerical values, we have our standard number of techniques, such as the mean, the median, standard deviation, and interquartile range, depending on how far your data is from being more or less normal. And of course, if you have multiple variables on those numerical scales, then we can think about correlation coefficients, but don't forget to inspect the scatter plot. So the next step will be inferential statistics. So as I already promised, the focus of inferential statistics is on inferring properties of a population based on a sample. And this essentially means that we are going to be testing a hypothesis. We are going to formulate hypotheses based on previous studies or previous literature, previous observations, and we are going to check whether those hypotheses hold for the sample we have derived. As I already mentioned, there are numerous tests which one can apply depending on the situation, and it's clearly not possible to discuss them during this lecture. So I would recommend you to check advanced books. And of course, whatever tests you are decided to carry out, it is important to understand what kind of assumptions the test makes. This might make your results valid or invalid. So after the break, we are going to go back to this example of different interpretations of the same emoji. And we are going to try to understand whether, based on the sample we have observed, that this emoji is interpreted differently by people of different genders in the population in general. See you in quarter an hour.
You are currently the only person in this conference.
Okay, can you hear me now? Yes, great. I'm very happy. So thank you very much. Let's take one step back. I apologize for this technical issue. So we've been looking at this table, right? You have seen it before. The question is whether we can infer based on this sample that the same emoji is being interpreted differently by people of different genders. So we are trying to make an inference on the population based on the sample. So we need two hypotheses. We need a null hypothesis, which is denoted H0, and we need an alternative hypothesis, which is denoted HA. So the null hypothesis is typically the default hypothesis. It assumes that there is no relationship between variables in the population from which a sample has been selected, or there is no impact of the intervention. So a null hypothesis is contrasted with an alternative hypothesis. And we are going to distinguish between those two hypotheses based on the sample data. So in this case, the null hypothesis for this particular test is that the interpretation of the emoji is not dependent on gender. The alternative hypothesis would be, of course, that the interpretation of the emoji does depend on the gender. So there are gender-related differences in interpretation of this emoji. So how are we going to work further? So first of all, we have our data. So this data is going to be fed to a test procedure. So a test procedure is an important part of a statistical test, which includes several elements. So the test procedure, it produces a test statistic. So essentially, it's a way to produce a single number based on a bunch of numbers. In our particular case, so when we start with the table we have seen before, we get, and our test procedure is chi-square, it will produce a number which is 14.3. Another important element of the statistical test is the distribution. Under the assumption that the null hypothesis is true, we know the shape of the test distribution of the test statistic. So the shape and the parameters of this distribution are specific to the test. In this particular case, it's a chi-square distribution with 7 degrees of freedom. I'm not going to discuss what those degrees of freedom are and where they come from. It's sufficient to know that they're coming from our data. So what are we going to do next? We are going to map this value we have computed for our test statistics for 14.3 and to our plot, and we are going to compute the area under the curve to the right of this value. So what essentially we are going to do, we are going to check how likely is it the value of the test statistic which has been obtained under the assumption that the null hypothesis is true. This is the famous p-value. So in our case, the value is 4.6%. So it is 0.046 chance that the value of the test statistic has been observed of 14.3 or higher under the assumption that the null hypothesis is true. So in this case, the value of the test statistics is lower than 5%. The value of the p-value is lower than 5%. So the test statistic in the 5% range. And 5% is a customary threshold. we can reject the null hypothesis. So this would mean that we do not believe that the interpretation of the emoji is independent from gender, and we actually believe that there are gender-related differences. Of course, as I already said, 5% is a common threshold. So the horror story of an empirical researcher is p-value being 6%. Essentially, it means that, of course, we cannot reject our null hypothesis. As I'm going to explain in a moment, the life is a little bit more complicated than comparing numbers to 0.05. But a very, very brief check. What exactly is the p-value? I mean, I hope you have seen it in your basic statistic course, but since you never know and so important, I thought I will repeat it here as well. So 4 options. Is it the probability that the null hypothesis is true? Is it the probability of obtaining the results, or more extreme ones, if the null hypothesis is true? Is it the probability that the alternative hypothesis is true? Or finally, is it the probability of obtaining the results, or more extreme results, if the alternative hypothesis is true? Go, 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 go. I mean, good news is that everybody who has answered so far has answered correctly. Bad news is that not everybody has answered. So I don't know what some of you are thinking. But let us hopefully assume that you are in agreement with the majority. So indeed, a p-value is the probability of obtaining the results, or more extreme results, if the null hypothesis is true. So the correct answer was B. However, you hopefully remember that I mentioned in the beginning that whatever statistical testing we are going to use, it is important to check what assumptions this test is making. So let us look at the data. Sorry. So one of the assumptions of the chi-square test is that the values of the cells should be 10 or more, and the expected values should be 5 or more. So in this particular case, we see that the values encircled in red are less than 10. This means that this assumption is violated. What is the impact? The impact is that the chi-square test is imprecise. There is an alternative, so-called Fischer's exact test. And you might recall the name of Ronald Fischer from the lecture on controlled experiments. This was the person who has written a book about design of experiments, and we talked about this book when we discussed Latin square designs. However, Fischer's test is computationally expensive and traditionally has only been applied for small tables and small numbers. So going beyond 2 times 2 tables was considered impractical. Luckily, we have computers nowadays. And of course, ideally, the results of the hypothesis testing for the chi-square test and Fischer's exact test should be the same. So this is my favorite statistical package, statistical tool, R. It is open source. It has a very strong community surrounding it, meaning that there are lots and lots of statistical tests which are implemented. But if you don't like R, you can always use other statistical machineries like SPSS or libraries such as scikit of Python. So what you see on the screen, it's exactly our example with the emoji. And I've been running 2 tests, chi-square test. which rejects the null hypothesis, and the p-value is 4.6. And we see the Fischer's exact test, which gives a p-value of 4.5%. So this gives us more confidence that our conclusion about gender-related differences in the interpretation of the face with the rolling eyes emoji is essentially true. Another observation I want to make here is that the workplace equals to E8, right? So it essentially means that in order to run the Fischer test on this very small example, I had to increase the memory beyond the default values. And actually, I had to wait for a couple of seconds. So Fischer's test is indeed computationally expensive. So it is plausible that sooner or later you will end up with a data set where you cannot apply it. And then the easier, more computationally efficient, but less precise Pearson's chi-square test might be useful. So we talked about this 5% threshold. Where does this magic number come from? And what can we actually do about it? So usually 5% risk is associated with a risk level of important, right? As opposed to something like severe or critical. In terms of losses, it is typically associated with something like less than 100,000 euro or some injuries, but no lives being lost. Still, it's very important to remember that the choice of the experimental design can influence our ability to detect phenomena, and we should not stare blindly at the data. It makes all the sense in the world to combine quantitative analysis with qualitative analysis, or maybe to combine different research methods to obtain the same conclusion in different ways. You might remember that we have called this kind of method triangulation, when we are looking at the same phenomena from different perspectives. Good. So let us move to the ordinal scale. So similarly to those minerals, in the ordinal scale, we have an order, but we don't really have distance. We cannot really say that the gypsum is related to fluoride in the same way as calcite to apatite. So usually when we are going back to the software engineering field, the ordinal scale data comes from surveys. As you might remember, surveys often employ attitude questions. So attitude questions give a statement and ask the respondents to express their agreement or disagreement. And this kind of questions usually are being referred to as questions on the Likert scale. So the scale is named after its inventor, psychologist Francis Likert. Lots and lots of people are pronouncing it as Likert, but as I have recently figured out, this is a mispronunciation. So Likert is the right pronunciation. So here is an example of a question, an attitude question from a survey of developers. And there are two categories of developers: video game developers, dark blue, and traditional software developers, cyan. The statement was whether the requirements are met in my software is highly subjective. So what we would like to do, we would like to compare the answers of the game developers with traditional software developers, and you would like to infer conclusions for all developers of those kinds, as opposed to specifically people who have responded to the survey. So again, this is a task for inferential statistics. Again, we are comparing two populations. And in this particular case, we are using a test which is known as the Wilcoxon exact test, due to Frank Wilcoxon, who actually was a chemist and not necessarily a mathematician. And he is credited for developing multiple important statistical tests. So in terms of procedure, it is exactly the same as a chi-square. We are entering our data into some kind of black box. In this case, the black box is a Wilcoxon exact test. It produces a p-value. We are comparing the p-value to our threshold. The common threshold is 0.05, and we seem to be happy. Essentially, we are saying that the null hypothesis can be rejected, the alternative hypothesis can be accepted. Moreover, there is even more good news. Wilcoxon tests, so the very same test, can also be applied to numerical values. So the effort you are doing now when learning about ordinal values can also be transferred to numerical values. So you might remember this R statistical tool I've been showing. So in the paper with Bogdan Vasilescu and his folks from University of California in Davis, we have looked how people respond to questions about R on the mailing list, R help, and on the Stack Exchange. So Stack Exchange is an umbrella name for a series of websites such as Stack Overflow you probably heard about, or cross-validated for statistical questions. So we have looked at the differences in time between when the question is being asked and when the first answer has been provided. So then we compared the speed of the time which is required to provide an answer on each one of the platforms. And to be really careful, we did not look at all people who are active on those mailing lists or on this platform, but only on people who are active on both platforms. So essentially, those are the same people in both groups, but in the group on the left, they are answering questions on the mailing list, and in the group on the right, they're answering questions on Stack Exchange. And we are using our wonderful Wilcoxon test, and we get this result. So the p-value here is too small to be computed precisely. This is how R reports it. Some statistical tools tend to claim that the p-value is 0 and put a small asterisk indicating that the value is too small to be computed precisely, because of course we don't really have real numbers in computers. Be careful though, p-values can never actually be 0. They can be too small to be computed, but they cannot be 0. So if you are writing in your report, be careful with this kind of report. So let's get back to our survey of game developers on non-game developers. So usually a survey is not limited to one question. In this particular case, the authors have asked 14 different questions. And you see here visual representations of the answers they have obtained. The upper row corresponds to the game developers, the lower row corresponds to non-game developers, and then for each one of the statements, we have a scale, like a Likert scale, from strongly disagree to strongly agree, from gray to blue, or from gray to red. So what could we do? We could, of course, compute 14 p-values corresponding to the Wilcoxon test, essentially apply Wilcoxon test to the answers obtained for each one of the questions. It seems very natural to select the p-values which are lower than the common threshold and report those findings as being relevant differences, statistically significant differences between developers of video games and developers of other kinds of software. Unfortunately, this would be wrong. The more inferences we are making, the more likely we are making errors. So if we are thinking about a threshold of 5%, this still means that there could be 1 out of 20 chance that this result was purely as a result of a statistical fluke. So there was no difference in the population, but our statistical hypothesis testing still claimed that there is one. Important thing, don't forget that statistical testing is not a black magic. I mean, it's kind of black magic, but not completely black magic. It can make errors. To make it even worse, if you are saying that we are expecting one error out of 20, this would mean that we expect 95% chance that our answer is actually correct. This looks like a lot, but since we are repeating this 14 times, the chance that there is at least one false positive is slightly more than half. So we can be pretty sure that one of our values is unreliable. One of our conclusions would be unreliable. So luckily, there are statistical methods that can help with it. So they are increasing the p-values to control for a false discovery rate. So there are multiple such techniques. Luca Pascarella and his co-authors, who are authors of this paper, have chosen the so-called Benjamini-Hofberg correction. I'm going to show you the results in a moment. So what's important to remember here is that if we are repeating the same kind of tests, if you are comparing the same population, maybe from slightly different perspectives, we are increasing the likelihood of inferring wrong conclusions. So we first of all compute the p-values and then we adjust them. This is the result of application of the Benjamini-Hofberg method. Again, it doesn't really matter how exactly Benjamini-Hofberg works. What is important is to see the original p-values in the second and the fourth columns, and the fifth columns, and the adjusted values in the third and the sixth columns for each one of those 14 questions. So you see that indeed the p-values have been increased. In particular, while analysis of the non-adjusted p-values might have led us to conclusion that there are 6 statistically significant differences between video game developers and game developers, after adjustment, only 4 of those conclusions remain. So again, if we are repeating our measurements, if we are repeating our tests, we need to be careful with adjusting the p-values. So the last part of the lecture will be, of course, dedicated to inferential statistics on numerical values. So we already have seen that the Wilcoxon test can be applied to numerical data. So we are going to take a closer look at comparing 2 distributions. So in general, statistical analysis balances 2 things. They're balancing assumptions we can make about the data and power of the conclusions which we can derive. So from this perspective, we are talking about parametric statistics and not parametric statistics. So parametric statistics tends to assumes that the sample data comes from a population that can be adequately modeled by a probability distribution that has a fixed set of parameters. This is the most constrained option because the assumptions are the strongest one, right? If we know, but it also means that we can infer the strongest conclusions. So if we know that our data comes from a normal distribution, we can infer stronger conclusions than if we don't know it. Non-parametric statistics does not make this kind of assumptions, but it also usually leads to weaker conclusions. So you need a stronger argument, stronger assumptions to derive stronger conclusions. So there's also something which is called semi-parametric statistics, which is kind of halfway. It combines statistical models that has parametric and non-parametric components. So here you see 2 distributions. They are very similar. One is represented by a black solid line. It's a density plot of the normal distribution with a mean 0. And the red dashed distribution is a normal distribution with a mean 0.11. So I have randomly sampled 1,000 data points from each one of those and have applied 2 statistical tests. One of them is the student's t-test. Another one is the Wilcoxon test. So you have already seen the Wilcoxon test. It is non-parametric. It does not assume anything about the shape of the distribution. The student's test, however, is only applicable if both distributions can be assumed to be coming, so if both samples can be assumed to be coming from the population with a normal distribution. In this particular case, you see that the data are such that using the student's test, we can reject the null hypothesis, saying that those two samples are coming from the same distribution. Using the Wilcoxon test, we cannot. So the student's t-test is more powerful. It can infer that the data comes from two different distributions. The Wilcoxon test cannot infer this. So again, why do we infer it? Well, so why do we use the Wilcoxon test in the first place? Well, of course, because in this particular case, when we've been talking about the time to respond, our data was really not normal. So how would we know that the data was really not normal? Those nice green things you see on the screen are known as the bean plots. So if you slant your head, you will essentially see a curve which is kind of similar to the to what we have seen on this large curve behind us. In a sense, it's also a probability distribution thing. But of course, you see that it is not symmetric and it has a long tail. So this is why we kind of suspect that the normality assumption of the student's t-test is not going to be satisfied by our green plots, by the data which has been used to create those green bean plots. As usual, merely looking at this kind of shapes might not be convincing enough, and we might like to perform a more careful statistical testing. There is a whole bunch of so-called normality tests. One of them is, for instance, Kolmogorov-Smirnov's test. Another one is Shapiro-Wilk test, and there are many, many more of them. So on the slide, you see application of the Shapiro-Wilk test to the data of the represented by this black solid line on the image behind us. So what is important in the normality tests is that the null hypothesis of the Shapiro-Wilk test is that the distribution is normal, and this is common for normality tests. So if the p-value exceeds the threshold, then the null hypothesis cannot be rejected, and then the parametric techniques such as student's t-test can actually be applied. So in a way, normality tests are upside down. They're kind of special. Usually when you are doing hypothesis testing, you like your p-values to be small, because then you can reject your null hypothesis and establish some kind of evidence. In case of the normality test, you usually would prefer your p-values to be high, because then this means that there is not enough evidence there is not enough evidence to reject the null hypothesis. So there is not enough evidence that would prevent us from using more powerful parametric techniques such as student's t-test. Good. So now the question is to you. On the right, you have a distribution of size in terms of source lines of code of C methods from a large corpus of open source data. On the left, you see the same for Java methods. The question to you, if you want to compare those two distributions, which statistical test should you use? Okay, so we have 2 people who say student's t-test and 4 people who say Wilcoxon test. So I have to disappoint you. It's a Wilcoxon test. If you look at the data, if you look at the axis, it's all logarithmic scale. So this means that our distribution is very, very far from being normal. It is completely skewed. So the assumptions of the student's t-test would not be satisfied. And we need to use a Wilcoxon test. So how is, what kind of statistical methods are in general used in software engineering? So here you see results of a large-scale literature survey very recently published. You see parametric test, non-parametric test in the first and the second row. You see multiple tests in the middle. I have not talked to you about effect size. And you see distribution tests in the last row. So there are different kinds of distribution tests, but normality tests are probably the most common species of those distribution tests. Essentially are tests which are checking whether your data can come from a distribution of a specific shape. So what is interesting here is, first of all, you see that the amount of statistical testing is increasing as we progress from 2001 to 2005. In particular, you see that the number of parametric tests is increasing. What is actually strange is that this increase in the number of parametric tests is not really accompanied by the corresponding increase in the number of distribution tests. And as we have seen in the previous discussion, before applying parametric tests, we actually need to perform a distribution test to ensure that our data does not violate the assumptions of those parametric tests. So strictly speaking, the numbers in the lower row should have been increasing much faster, but somehow it does not happen. So the last topic I would like to discuss with you is the impact of time. Sometimes merely comparing 2 groups is not enough. When we are studying a region, when we are studying a subfield of empirical software engineering which is related to software evolution, we need to take into account time, and we also need to take into account interventions. So what are interventions? Interventions are changes which have been induced in an ongoing process. For instance, you had a project that used subversion, suddenly you are using Git. You have introduced a continuous integration solution such as Travis CI. Or maybe you have introduced a bot which reports coverage. So we would like to know whether this kind of interventions are beneficial for the software development process. And of course, the way to, in order to understand what is beneficial and what is not beneficial, we need to measure it somehow. How can we do it? We are going to look at the results before and after. This is an artificial example. You see here change in the slope, but the t-test, even though the conditions are satisfied, the assumptions are satisfied, is not capable of distinguishing between the 2 situations because it does not take explicitly the impact of time into account. Again, this is a situation when we have a change in level. So the slope is the same. We had an increasing process. We still have an increasing process after the intervention, but the intervention significantly reduced the level. Again, there is no way to observe this difference using a t-test. So to address this kind of challenges, there are many statistical methods which apply to so-called interrupted time series. So if you want to know more about time series, there is a separate course in statistics from Q4. But Today I'm going to discuss only one of those tests, and this is a so-called regression discontinuity design. So regression discontinuity design is a variant of multiple regression. I hope you remember what regression is from your basic course, which takes into account explicitly time before the intervention, time after the intervention, and the intervention itself. Let me show you how it works. So here we have our artificial data. Time is going from 1 till 200. Time after intervention, of course, starts only after the intervention. And time and intervention itself, it is a binary variable which is flipped to true from the moment of the intervention itself. Again, it can be an introduction of Travis, it can be an introduction of bot, or change of, for instance, a license. So from the perspective of statistical modeling, this then becomes the following formula. When we have coefficients associated with time and time after intervention, we have the impact of the intervention itself, and of course, we also have the epsilon, right? We have errors. We have residuals, right? So in this particular case, we can fit the data to our, we fit the model to our data. We observe that beta, so the slope before the intervention is almost 1. The slope after the intervention is roughly minus 0.5, and the gamma is roughly 50 units. So why is this approach so popular? Is because it allows us not merely to understand the impact of time, but also the impact of time in combination with additional independent variables, which will simply be included among the betas. So this method has been successfully applied in series of papers that have studied impact of introduction of continuous integration, introduction of bots, change of the license, introduction of a different issue tracker, so the change from Bugzilla to Jira, and so on and so forth. It's a very popular statistical technique. So let me just show you what kind of conclusions we have derived using this method. So for instance, before the introduction of Travis CI, we have observed that more and more issues were closed. More and more issues and pull requests have been closed on GitHub. However, introduction of Travis has slowed down this trend. When it comes to, for instance, time which is required to resolve pull requests, so essentially to decide whether those pull requests have to be merged or not, the time was increasing before the introduction of Travis CI, and it flattened out by Travis. So essentially, the introduction itself did not affect the duration, but at least it stopped growing. And the last interesting observation was that the number of comments, the amount of communication was decreasing. Essentially, this means that developers have been performing a comparable amount of work. They've been essentially closing the same things at the same smallest at the same speed, but they have been talking less because Travis CI has taken over the role of the silent helper of flagging what is going on and what is not going on. So to summarize what we have seen, we have looked at 3 types of variables: nominal, ordinal, and numerical, meaning interval, ratio, and absolute. For each one of those, we have discussed methods for descriptive and inferential statistics. For example, for the inferential statistics for the nominal level, we have seen chi-square test and Fischer's exact test. For the ordinal, for the descriptive level, we have seen Cohen's Kappa and weighted variant of it. We have also seen Wilcoxon Tests, which can be applied both to 2 ordinal values and to 2 numerical values. We have seen t-test, which is more powerful than a Wilcoxon for numerical values, but makes more stringent assumptions. And finally, we have seen regression discontinuity design, RDD, which is necessary if you want to understand impact of time, time alone, or time in combination with other independent variables. So obviously, there are many, many more techniques, and I already mentioned it. There are many more statistical tests. You should not assume that the overview I have provided is complete in any sense. It is merely a small primer, small introduction to this field, which I have selected based on partially techniques I see in current software engineering research, and partially techniques which I like to apply in my own research. You see here a couple of books you might consider checking. Alana Gresti, Categorical Data Analysis. It's essentially all about nominal and ordinal variables. Parametric and non-parametric statistical procedures by David Cheskin. It's a cookbook. It's really a cookbook. It has chapters for individual tests with small examples, with explanation, and so on. A very interesting book of I already mentioned when we talked about interviews. Has a chapter about statistical methods, and of course the book of Shadish on experimental and quasi-experimental design for generalized causal inference. Good. This concludes our discussion for today. I apologize for technical issues with me recording it and losing the sound at some point. I hope that it did not disturb your experience too badly. In any case, the video will be made available both on Canvas and on YouTube on our regular channel, and I will also upload the slides on Canvas. Thank you very much, and goodbye.